Alright, we're to find the value of the constant k so that the three vectors a, b, and c are coplanar. And so for three vectors to be coplanar, what coplanar means is that they're on the same plane. Now, the same plane now if they're on the same plane, there is a parallelepiped that is determined by the three vectors. Okay, this parallelepiped determined by the three vectors has a certain volume. If the three vectors are in the same plane, then the volume of this parallelepiped will be 0. If coplanar. If A, B, and C are coplanar. Makes sense. If they're all on the same plane, you wouldn't have any height to that parallelogram prism, and so if A, B, and C are coplanar. Alright. Now we have a way to calculate the volume of this parallelepiped, and it's called the scalar triple product. The volume of that parallelepiped is found by taking the vector A and dotting it with B cross C. It's called the scalar triple product, and we can actually work this out for these particular three vectors with the individual components that they have, but we found that there's actually a better way to calculate that number. Take the coordinates of A, or the components of A, make them the first row in the matrix, components of B, second row in the matrix, components of C, third row in the matrix, and find the determinant of the matrix. Now what we're going to do is we have this constant k. Okay, we have this constant k that we need to find. Let me write it in a different color so that the volume is 0, or that they are coplanar. Let me go back and that's supposed to be an A and an R there, sorry. Coplanar. And so we have this determinant that we have to find. We can use cofactor expansion on the first row, or actually any row or any column. We have another way, a shortcut, where we copy down the first column, copy down the second column, and do it kind of like we do a 2x2 by calculating products along diagonals. And so there's the forward-facing diagonals. We multiply along these diagonals, take those products, and get 0 minus 16, there's 3 negatives there, and 12 and 8, that's 96, minus 96. That's the forward-facing diagonals. Then we have the backwards-facing diagonals. Multiply along these guys. Be careful with the signs, with all these arrows drawn in. It's easy to make a mistake with the signs, but we'll have an 8k positive. Oh, that 4 is not negative. I'm sorry. That 4 is positive. So that was a negative 96. Okay, we're good. Sorry about that. And now this is actually a negative 8k. And then we have a positive 8. And then we have a 0 for the third diagonal. So if you draw on the lines, it kind of obscures, and it's easy to make a copy down mistake as well. the first part gives us negative 112, and then we add on the 8k, and we take away the 8. That is what the volume of the parallelepiped with these three vectors would be, and we want it to be equal to 0. So we go ahead and set this equal to 0 and solve for k. So basically it's that 8k is 120, or that k is 15. Dividing by 8 tells us that that k is equal to 15. When k is 15, the three vectors will be on the same plane. The parallelepiped will have 0 volume. The scalar triple product will be 0.